So now we're going to look at the ways in which kinetics can help us understand the mechanism of a reaction. And there are two possible ways that we'll look at. The first is if we have a slow step followed by a fast step. Now, recall, this is the overall reaction. NO2 plus CO yields NO plus CO2. And you go into a laboratory and you do the kinetic studies and you find out that the observed rate equals a second order reaction, second order in NO2. So you go back and you think and you scratch your head and you come up with elementary reactions that will add up to give the overall reaction and hopefully will sustain the observed rate law. So here's one example. NO2 plus NO2 yields first NO3 plus NO. And this is a slow step, and the rate equals K times the concentration of NO2 to the second power. We can write this rate law because this is an elementary reaction. You can write rate laws from elementary reactions. You can't write them directly by looking at an overall reaction. You have to go in the lab and prove it and do it. But in elementary reactions, you can write a rate law based on the elementary reaction. The second step is that NO3 reacts with carbon monoxide to form NO2 plus CO2, and the rate for that is this, and that's the fast step of the reaction. But the thing is, you have a slow step followed by a fast step. So the thing that's really determining the rate of the reaction is the slow step, because the fast reactions that follow the slow step are not going to impact the rate of the reaction. Only the slow step in this situation is going to do that. So it turns out that our elementary reaction happens to coincide with what we observed in the laboratory, and that validates this particular idea of these two elementary reactions being the mechanism for this overall reaction. Now, if we take a look at an energy diagram for this mechanism, what we see is we have a high activation energy first. That corresponds to a slow step because, remember, the higher the activation energy, the slower the reaction is going to be. In the fast step, you have a much lower activation energy, and that does not impede the rate of the overall reaction. Only the slow step does that. That's how it works. The first step is slower than the second step because its activation energy is larger. And the first step in this mechanism is the rate determining step. And the rate law of the first step is the same as the observed rate law of the overall reaction. Now, what if we have a situation where we have a fast initial step followed by a slow step? Well, it's a little more complicated than if we just have a slow step followed by a fast step. When a mechanism contains a fast initial step, the rate limiting step may contain intermediates or unstable species. And when a previous step is rapid and it reaches equilibrium, the forward reaction and the reverse reaction are occurring at the same rate. That's why they're at equilibrium. So the concentrations of reactants and products of the step are related. You can write rate laws in both directions. And the product is an intermediate. And then if we substitute into the rate law of the rate determining step this information we just learned, it'll produce a rate law in terms of just reactants. So this is much better understood by actually seeing a situation like this, and Here is one. We have a reaction. We go to the lab. 2 hydrogen molecules react with 2 nitric oxide molecules to form 2 water molecules and nitrogen gas. The observed rate is a third order overall reaction, first order in hydrogen and second order in nitric oxide. So how does it work? So here's the first step. 2 nitric oxide react to form N2O2, and in turn N2O2 disintegrates into 2NO in the reverse reaction. So the forward reaction and the reverse reaction are occurring at the same rate at equilibrium. The second step would be a slow step where hydrogen and N2O2 reacts with water to form N2O. And for that, we can write a rate law. Finally, we have hydrogen and N2O forming H2O and N2, and that's a fast step. Since that fast step follows the slow step, we don't need to do much with it. For step 1, at equilibrium, the rate of the forward reaction equals the reverse rate. So that K1 times NO squared equals K minus 1 times the concentration of N2O2. Now what we're going to do is solve for N2O2. That's the intermediate in this reaction. And all we do is rearrange to put the K minus 1 dividing into the K1. Bring it over to the other side. So now we have the rate law expressed in terms of the intermediate. Now, for the slow step, we have this reaction, and as you see, we have the intermediate in that rate law, and what we're going to do is substitute this equivalency for the N2O2 because that's an intermediate and it's not going to stick around. So we'll just take this and substitute it for the N2O2, and what we'll end up with is this. And we can combine all of the rate law constants into one rate law constant. And we end up with a rate law that validates the mechanism because it agrees with the rate law determined by experimentation. So here's another one. You have ozone decomposing to oxygen molecule and atomic oxygen. That's the fast step. And it's followed by the slow step. Ozone reacts with one of these oxygen atoms to form 2 molecules of O2. So the intermediate is the oxygen atom. And when we add them together, we get an overall reaction, and the intermediate is canceled out. Now, for step 1, the rate of the forward reaction equals the rate of the reverse reaction. So we can write the rate laws for the forward reaction is a rate law constant times ozone equals the rate law constant for the reverse reaction, second order, times oxygen and atomic oxygen. We solve for the intermediate, atomic oxygen, and we get this. And now we return to the rate law of the slow step, and for atomic oxygen we substitute what we just solved atomic oxygen to be. Plug that in and solve, and what we end up with is this rate law right here. And of course that it would be answer B. Rate equals K times ozone squared times oxygen minus 1. Now we're going to talk about activation energy. The energy barrier to a reaction is called the activation energy. It's the amount of energy needed to convert reactants into an activated complex. The top of the hill, so to speak, before the reaction can proceed to the products. The activated complex is a chemical species with partially broken and partially formed bonds. So here's a couple of examples. Which graph do you think would be consistent for a reaction in which the first elementary step was the fast step, and the second is the slow step. Well, if you chose B, you'd be right, because it has a lower energy activation. That would be the fast step. The second one would be the slow step, because it has a higher activation energy. So changing the temperature changes the rate constant of the rate law. And Arrhenius investigated this and showed a relationship involving the energy activation. So the natural log of the rate law constant equals minus E sub A over R times the inverse of the temperature, the absolute temperature, plus the natural log of A, where R is the constant, 8.314 joules per mole K. A is a factor called the frequency factor, and E is activation energy, the extra energy needed to start the molecules reacting. The frequency factor is based on the probability of correct particle orientation that leads to successful collisions. Not every collision is going to lead to a product. There's going to be a proportion of collisions that don't. That's taken into account in the frequency factor. So here's a question: determine the activation energy and frequency factor for the reaction ozone forming oxygen gas plus atomic oxygen, given the following data. So here's temperatures, and here are rate law constants at different temperatures. And if we plot those data using the Arrhenius equation, where y represents the natural log of the rate law constant, and the horizontal axis x is 1 over the temperature, and we plot the data, then we can figure out the energy of activation for the reaction. Now let's go over a question that I could ask you on an exam. Determine the activation energy and frequency factor for a particular reaction here. We're going to use the Arrhenius equation. We have the Arrhenius equation in the format y equals mx plus b. So let's just parse this out and show you how these data are displayed on the graph. First of all, the natural log of k is the y-axis here, all right? And 1 over the temperature is the x-axis. And the slope, m, is equal to minus E sub A minus the activation energy divided by the gas law constant. And of course that's rise over run. Because we have a line pointed downward, it's going to have a negative slope when we figure out the slope. So we have to have a correction factor for that so we don't end up with a negative energy of activation. That's what that negative sign is doing there, to correct for this negative slope. So that's how we can calculate the activation energy. The slope equals minus E sub A over R. If we rearrange that, minus times m, which will be a negative number, times r is going to be equal to the activation energy. Finally, B represents where the line crosses x equals 0, which is right here. And that number is going to be 26.8 in this graph. The slope in this graph is minus 1.12 times 10 to the 4, and that's equal to minus E sub A over R. All right, so we've set it up for you. Get your pencils, get your calculators out. Here it is again, y equals mx plus b. Here's the slope, here's the y-intercept, and go for it. Figure out what the activation energy is and then the frequency. Turn the playback off. See if you can get the same numbers that I will show you as soon as you come back on. Okay, so here we go. You've calculated it now, and for E sub A, that's going to be equal to minus a slope, which is a negative number, minus 1.12 times 10 to the 4 K, and the gas law constant. Multiply that, and you'll end up with 9.31 times 10 to the 4 joules per mole, or 93.1 kilojoules per mole. So there's your activation energy. As for the y-intercept B, you're going to need to take the anti-natural log of 26.8. So you set that up. Every calculator has a natural log button, and probably second function is the e sub x button, and that's the one you'd use. You'd enter 26.8, and then second function, so you get the e to the x, and you take the anti-log of it, 4.36 times 10 to the 11, and there is your frequency factor. There is also a two-point form for this where you don't have to plot a graph to get the energy activation. The form of this, which will be given to you, is as shown here, where R equals the gas law constant. The reaction 2NOCl yields 2NO plus Cl2 has an energy activation of, 100 kilojoules per mole and a rate constant of 0.286 at 500 K. What is the rate constant, K, at a temperature of 490 Kelvin? So you should be able to figure that out. Okay, that's it. Thanks for watching.